discussion in the chat.
Hello, everyone. First of all, I would like to thank the organizer of the Alife 2020 conference for giving me an opportunity to talk here today. I will present our paper, The Effect of Mutation on Equilibrium Properties of Deterministic and Random Evolutionary Games. We consider an infinite population that consists of n matrices from 1 to n. Their frequencies are given by x1, x2, and up to xn. The replicator-mutator equation are a set of n ordinary differential equations that characterize the evolution of the frequencies. In this equation, this equation shows the evolution of the frequency xi. On the right-hand side, fj is the fitness of or average payoff of the characterize j. qji is the probability of a player using characterize j change to the characterize I. And f bar is the average fitness of the population. The key in this equation is that it takes into account both selection and mutation mechanisms. When there is no mutation, that is when the matrix Q becomes the identity matrix, the replicator-mutator equation reduced to the replicator equation, the second equation in the slide. We consider the case of D player and two strategies. Suppose the two strategies are A and B. To determine the payoff matrix, we consider all possible interaction. For example, AD-1 is a payoff of the strategy A when interacting with the group of all other A player. And AD-2 is a payoff of the strategy A when interacting with a group consisting of D-1 other player that have D-2 A player and 1 B player. Similarly, we can compute the payoff for the strategy B. From the payoff matrix, we compute the fitness of two strategies A and B. Simply, they are the average of payoff when considering all possible interaction in the population. FA and FB are given by this formula. In the case of D player and two strategies, we call X the frequency of strategy A. Then the frequency of strategy B is simply 1 minus X. And the replicator-mutator equation, in this case, characterize the evolution of X. It depends on Q, that is the mutation, and FB and FA, that is the fitness of B and A. When Q equal to 0, that means there is no mutation. Then we obtain the replicator equation, the second equation in the slide. We are interested in random games where the payoff entry AK and BK are random variables. Random games are important when modeling systems that have uncertainty. For example, there is not enough information, or when the environment changes quickly, that the payoff entry cannot be assigned deterministically. We are interested in equilibrium points of the system. Equilibrium points are those points that make the right-hand side become 0. So the last equation in the slide. Studying equilibrium points for dynamical system are important. It predicts the coexistence of different strategies in the population and provide information about the maintenance of polymorphism in the population. Due to the randomness of the models, we are interested in two important questions. The first question, what is the statistics of the number of equilibria in a multiplayer random game? The second question, what is the effect of mutation? We consider first the case of replicator equation, that is when there is no mutation. And in this case, x equal to 0 and 1 are two equilibrium points. We are interested in a non-trivial equilibrium point between 0 and 1. And it satisfies the equation FA equal to FB, that is when the two fitness are the same. So we obtain this equation, this polynomial equation, where beta k is the difference of the payoff and t is a fraction between x and 1 minus x. Previously, there are many papers studying equilibrium for the replicator equation. These papers directly show this polynomial equation, and therefore, by unbend impossible theorem, they cannot solve this equation when d greater or equal to 5. So the direct method is limited to small group size. To overcome this difficulty in our papers, we connect to random polynomial theory. First, we answer and we study the statistic of internal equilibria in D-player and two strategy games. We obtain quantitative bounds of the expected number of internal equilibria, both lower bound and upper bound. In particular, we obtain the asymptotic behavior of the expected number of internal equilibria when D, the group size, tend to infinity. We also can characterize and compute the probability that the game have any m internal equilibria. Using the formula, which is quite complicated, and I do not show here, we compare our analytical reason with a simulation, which is shown in this table. The two agree with each other. Now we consider the replicator-mutator equation, that is when there is mutation. We consider the simple case when there are only two players and two strategies. We call strategy C for cooperation and D for defection. The payoff matrix in this case given by this table, the 2 times 2 matrix. And the equilibrium for two player and two strategy game is given by this cubic equation. It depends on T, S, and the mutation Q. We consider 4 popular social dilemmas depending on the ordering between T and S: the prisoner dilemma, the slow deep game, the Stag Hunt, and the Harmony game. We also consider where T and S are random variables. Our main reason is the following. Suppose that S and T are uniformly distributed in the corresponding intervals. Then we provide explicit formula for P1, P2, and P3, which are the probability that a game have 1, 2, or 3 equilibria. We observe here that the Stag Hunt and the prisoner dynamical game are more interesting when P2 and when the probability P2 behave very nicely. We also compare our analytical reason and sampling to show the effect of mutation for all of the games. Here we plot for 3-game prisoner dynamic, Stag Hunt, and slow deep game. We clearly see the influence of mutation in the distribution, in the number of equilibria in social dynamics. This means when we have mutation, the diversity increase. To summarize, we have studied the replicator-mutator equation, which is a fundamental equation in evolutionary game theory and population dynamics. We study statistics of number of internal equilibrium and the effect of mutation. Our key method is connect random polynomial theory to evolutionary game theory. For future work, we wish to extend our methods to more complicated models in evolutionary game theory and population dynamics. With this, I would like to finish my talk, and thank you for the attention.
And thank you to all the speakers in this session. This was our last talk for the day. Thank you so much for being here. If anyone has a question, I know I'm curious about random polynomials, so I'll probably reach out to Hong on Slack, and hopefully we can keep some of the conversations going on there about all of your talk. This was great. Thank you so much for being here.
Hi, everybody.
Bye.